Okay, are we ready? All right, thank you very much for having me here. Great conference, nice t-shirts. So I'm Sergey Matsevich from Microsoft Cloud and Information Services Lab. And today I'll tell you about the new algorithm for topic modeling and also share my experience on how we implemented that on top of Apache REEF. It's a very nice framework, also originated in our lab, and now it's an Apache incubator project. So it's been the work of many people from UC Irvine and from our lab, and also lots of contributions from REEF collaborators worldwide. Thank you very much, guys. So here's the brief outline of the talk. So first I'll explain what topic modeling is, what is the problem we were trying to solve. Then I'll give you an introduction on what is state of the art in topic modeling. And then we'll discuss my algorithm. And the second half of the talk will be about the engineering part of things, how we implemented that on top of Apache REEF, and I'll share the results. So what is topic modeling? The problem is the following. Given the collection of documents, we want to reveal hidden topics, what each document is about. So we can look at the newspaper article and automatically infer that this article is, say, 60% about sports, 30% celebrity gossip, and 10% politics, for example. So given no labels, no other information than which words appear together in each document. So here's an example. It's a small a small corpus of 2,000 movie reviews from Usenet. And here are like just first sentences of 2 random movie reviews. And if you feed this data through the algorithm, you get the following. So for each movie, you have this nice histogram that shows you what is the topic distribution for that particular movie review. And you can easily see that the first review is actually about some horror movie, and the second one, you can see this big spike on the bottom. It's actually Pixar and Bug's Life, so it's like Disney animated movie. And so here, notice that some topics are common here. So some reviews can share a topic. So the second topic is, I guess, some general topic about movie reviews. And the words can also belong to more than one topic. So say, for the first 2 topics, the film appears as a film in general. And on the first one, it's also like a horror film. And similarly for action, you can see that there's like a Jackie Chan type of action movie, and also like a crime and cop type of action. So, and if you look at the topics, again, here's an example, 2 topics that I picked from the same corpus. You can see that the first one has words like Jackie Chan, Hong Kong, Van Damme, action. So it's this Chinese martial arts type of movies, I guess. And the second is very clearly sci-fi. So we can represent the input data. So how do we model the data? So the simplest model is the following. We can build a huge matrix where each row is the document and each column is the word in the vocabulary. And then every cell in this matrix is basically how often a particular word occurs in a particular document. And we can decompose this matrix as a product of 2 smaller matrices, one for topic proportions for each document, and another one is for word membership. What is the probability that the word occurs in a certain topic? And then every element in the input matrix can be represented as a dot product of this topic proportions and the topic word membership. And notice that the position of the words in the document do not matter. So it's so-called bag of words model. And also, it is very important to understand that this is to distinguish the model and the inference algorithm. So this is how we model the data, and this actually has many variations on the models. So say, for example, if we want to do hard clustering, where each word belongs to one and only one topic, then this word membership matrix will have in each column all zeros except exactly one element, which will be 1. There is also another popular model called LSI, Latent Semantic Indexing, or it can be an arbitrary matrix. In our case, we assume that the words are drawn from unknown Dirichlet distribution. So this matrix is column stochastic, so all columns add up to 1. And this model is called LDA, latent Dirichlet allocation, because of that. And again, like position of the words don't matter, so it's all, yeah, so, you know. So it's all bag of words to me. Sorry, Mr. Tolstoy. So state of the art currently seems to be Monte Carlo methods, and most notably collapsed Gibbs sampling is the most popular approach. In this approach, so this is how you do inference. So like given the model, how you do the inference. So collapsed Gibbs sampling basically works the following, right? You assign topics to each document, each word at random, and then you go over and over this corpus again and again, and you adjust topic for each word conditioned on all other topics that you've assigned to other words. And if you do it repeatedly, you converge to some local optimum that actually reveal the topics. So you can parallelize it to some degree. So you can do you can process documents in parallel, but there is still some data that you have to share across all the workers. Most importantly, this word topic table. So, and that gave rise to all sorts of optimizations like parameter servers, for example. And most recently, like just 2 weeks ago, it was presented a new approach called Light LDA. It just 2 weeks ago on it was presented, and it's basically also a Monte Carlo method, but they use Metropolis Hastings sampler, and which with better proposal distribution, and they also use some high performance parameter server. So it's parallelizable to some degree, but it's not embarrassingly parallel. Well, our approach is more embarrassingly parallel than theirs. So, so what we do, we use completely different approach to do this factorization, and it's called the method of moments. It's actually a pretty old algorithm. It was invented by Carl Pearson in like 1894. So new is well forgotten old. So the first 2 moments of distribution, so the first moment is just expected value of your random variable. So for the corpus, it will be just probability of the word in corpus. And sufficient statistics is just the count of the words in the corpus. And for the second moment, it's a covariance matrix. It basically says how frequently a pair of words occur in the same document. And people use that, and actually for the second moment, it should not necessarily be, it can be any similarity measure, and people use that for graph clustering, for example. So you can have a graph Laplacian, and then that actually leads to spectral clustering for graphs. And, but this, so it's closer, but it still does not give us a mixture of topics that we want for the document. So we probably have to look at the triplets of words, right? But how do you do this? Now we have a third dimension. So to capture triplets of words, you have to have a cube. And this is where tensors come into play. So, well, we need to go deeper. So the 3 moments, hey, come on. So the 3 moments are gonna be the expected value of the word, the co-occurrence of pairs of words, and also co-occurrences of triplets of words in the same document. And it was shown that if you add some shift terms, actually if you squint right, you can see that the second moment here is nothing but a covariance matrix plus some shift term that actually works as a Dirichlet prior. So basically it's like some hyperparameters that specifies how sparse your distribution of topics is. And similarly for third moment, there's a whole bunch of correction terms that won't fit in the slide, but it's basically very close to skewness plus some shift terms. And so it was shown that if you collect this information, it will be sufficient to reveal the topics. So we have the information, right? How do we get the topics from there? Again, we show that you can, given the tensor, you can represent this tensor as a product of 3 matrices, as a cross product of 3 matrices, that an column of the matrix will be actually the topic. So it's very similar to eigen decomposition. So you can think of it as like spectral decomposition of a tensor. And okay, fine. So now we know which data to collect. We know that if we decompose the tensor, we'll get the topics. How do we do the decomposition? Well, we use, oh yeah, so this is actually how it looks like. So every element of the tensor can be represented as the cross product, as a linear combination of cross products of 3 vectors. And in our case, all those 3 vectors will be the same because basically like order of words don't matter. Okay, and for the decomposition, we use alternating least squares. So we basically start with 3 matrices that we initialize as random matrices, and then we use 2 matrices out of 3 to infer the third one, such that they approximate the tensor, and then we switch. Then we keep the one that we just generated and use that plus the other one to infer the other one. And we keep iterating like that. And that actually gives us desired decomposition of the tensor. And yeah, so that basically gives us an algorithm. So now we have, on the input, we have our corpus of D documents and the fixed vocabulary size n. And we specify in advance how many topics we want to discover, okay? And also some Dirichlet hyperprior that specifies how sparse the topics should be, okay? And notice that the tensor is actually extremely sparse, even for covariance matrix. Like, first of all, it's symmetric, right? So that gives us a lot of savings in space, knowing that it is symmetric. And similar for the tensor, it's sparse and it's hypersymmetric. So it basically, like, for any permutation of indices, you get the same value. So we can use that to our advantage. So we can do eigen decomposition of the second moment and use those eigenvectors to project our tensor into lower dimension space. And then we use alternating least squares in this lower dimension, and it actually saves us a lot of memory. And then eventually, all we have to do, we just have to project those eigenvectors into ambient space, and we have the topics. So that's basically the whole algorithm. So you can notice that, first of all, the computation goes in stages. So on every stage, we produce some data that is used on the subsequent stage. So the stage is a linear. So it's like a linear DAG, just a path. And on each step, we have to carry over the data. So it would be nice to keep this data in memory. So we want to retain the resources, and we want to keep the results of the computation and pass it on. And yet, alternating least squares is the most expensive step. So this is where all the optimization really, like every optimization really pays off, because typically we have to run like 200 to 300 iterations to get the results. And luckily, it's highly parallelizable. On each step, we can process slices of the tensor independently. So we have k-way parallelization. And so basically, we can produce one slice of a tensor and produce one row of the resulting matrix. And all we have to do, we have to collect those rows, normalize the columns, and that gives us a new matrix that we have to broadcast. So we have to synchronize on each iteration. We have to collect the results, build a new matrix, and then broadcast it back to the worker nodes. Okay. So this is actually where REEF framework comes in very, very handy, because we have, first of all, it's a very simple API. So it's all event-driven. So all you have to, like, all control flow is basically firing the events and registering for some events in the system or in your code. And it also allows you to retain the resources and gives you very fine-grained control on like how flexible you want to be in terms of resources, so you can request more resources and release some resources as you go, so you can be very elastic. And in our case, it's very handy because we can retain the resources and keep the results of the computations that we get on one step and pass it on to the next step. And also, it has a very powerful inter-process communication library. So it's very similar to MPI API. So we can broadcast the model, we can collect the results, and it works pretty well. And last but not least, we use the dependency injection in distributed setting. And this actually saves us tons of boilerplate code that you usually have to write to validate your configuration and check for errors on the other side. So that was a very nice feature that we used. So here's the place of REEF in the Hadoop ecosystem. So it's basically a so we usually advertise it as a standard library for big data. So it's a thin layer on top of Resource Manager that first isolates you from Resource Manager. So currently we support Yarn and Mesos. And you can also run REEF application locally. So you can just, in this case, we just start a few JVMs on your laptop, and they just communicate with each other. So it's like really easy to debug. You can attach to the process, and it's like really, really handy. So you don't have to have Hadoop on your machine to actually run the code for REEF. So, and on top of REEF, we have a few handy libraries for like dependency injection and inter-process communication. And so basically, this is the library. So it's lower level than Spark, but this is the library where you want to use if you build the next Spark or the next DES or something like that. So I'll give you more details now. So in the following slides, I'll use the following notation. So this grid on the right is actually, assume that this is your grid. We'll talk about Yarn. And every rectangle here is actually, every rectangle is a container. Container is a slice of the machine. So it's some fixed amount of resources that the resource manager allocates for you. So it's like fixed amount of memory, CPU, bandwidth, maybe some other resources like FPGA or GPU or whatever. Okay, so this is REEF. Hello, this is REEF. Your battery is running low, probably. Okay, so this is our Yarn grid. I don't really know where to point this thing to. All right, anyways, so this is our grid, and say we have some data on HDFS, and we'll assume that we use Yarn, and so when you start REEF application, the first thing we do, we allocate one machine on the grid that will be managing all the control flow and error handling, and we call that the driver. So the driver is the machine that actually requests resources from Yarn, and so this is how we start. So we request resources. I would say I need 3 containers that have my data, and also plus 1 container more that will coordinate the computation. And REEF responds back to, guys, this is. Okay, so Yarn returns back the resources. And the first thing we allocate on the containers, we call them evaluators. So you can think of it as the preemptible JVMs. So those are REEF processes that will run your computations, and they also keep data in memory that can be passed from one stage to another. And eventually okay, so this is a disaster. Come on. Sorry. Hey guys, so how do I fix? Hello? Oh, now it works. Okay, now it works. Okay, so you have your evaluators, and now you can submit the jobs to it. Oh, now it works. Okay, so this is where you submit the tasks, and they perform the computation. And let's say one of the containers fail. One of the containers fail. Yes, so you submit the job, and one of the containers fail. In this case, your driver will receive the notification. Say, after a few missed heartbeats, your code will be notified that there is a failure in the system. And now it is up to you to decide what to do in this case. Let's say we want the new resource from Yarn. Come on. So we ask Yarn for the new container, and Yarn responds back, and we fire new tasks there, and we just continue. Eventually, all the tasks complete, and they signal their completion to the driver, and the driver submits the new task, and this is how it goes. So every stage goes like that. Eventually, all the tasks complete, and then we can release the resources to Yarn, and eventually the application ends. So here, this control flow is like really easy. And actually, like if some of you did Erlang, like it's similar to Erlang OTP, where business logic and the control flow and error handling are decoupled from each other. So say, if exception happens in the worker and you don't catch it, it will be thrown all the way to the driver. And in the driver, you will handle all the errors and decide what to do in this case. So it's very, very handy for like centralized error messaging and control flow. And it's also very scalable because we don't have to do much. All we do is just like sending messages and register for the events. And REEF itself is pretty stateless. So all the state is in the driver, and it's in user code. And again, you're very flexible on how to do with that. You want to persist this or not. So REEF itself. So this is how it looks in code. So we just register, and this is actually just those two handlers. This is all we have for the Tensor factorization code. So we just register for the event, and then we fire, like, active context is the event that signals us that the resource was, the container was allocated. So we can submit the task to this evaluator. And similarly, when the task is finished, we can submit to the same evaluator the next task in our pipeline. So very handy. Another cool feature of REEF is dependency injection. It's actually an independent library. You can use this independently of REEF. It's called Tang. So what is the problem that we're trying to solve there? It's basically distributed configuration. So if you try to run things on bare Yarn, you know that this is very hard. So you have to submit your jars and executables to every node, and then you have to, every individual node has usually different configurations because you have to specify which particular slice of the data you want this worker to work on, and maybe some identifier and stuff like that. And if you make a typo, you submit this job to 100 machines, and then all they fail, and this is when you, and sometimes you don't even have the logs because they were not able to read the configuration and decide like where to write those logs to. So in our approach, we use dependency injection. So we piggyback on the Java type system to, okay, for Haskell people here, Java type system. So to do as many checks as possible before we submit the configuration. So here we annotate so this is again like real code from the Tensor factorization. So we annotate the constructor as injectable. And for leaf nodes of the configuration, we use this parameter annotation, and we use classes, like real Java classes, as identifiers for the parameters. And that actually allows us, first of all, to check for typos. And second, is actually very handy in your IDE because you can autocomplete, and it fills up suggests which parameters to use. And the remaining 3 parameters are also injectable, so you just magically get the instances in your constructor. So you can see that the group communication library, you can just inject in your constructor, and you have it. And similar for the data, we automatically partition the data for you, so you'll just have this data loaded already, okay? So similar for group communication, so it will be an injectable object, and it provides a very powerful API that is modeled after MPI, but not quite, because the main limitation of MPI is that MPI is not elastic. So if, first of all, you have to know in advance how many machines you will allocate for the MPI, and each machine has assigned identifier, and if some machine fails, this is it, the whole cluster fails. So on the other hand, MapReduce is elastic, but you cannot have logic like during the runtime that will adjust your resources, like request more, or I know Spark, recent version of Spark has something like that. So here's our approach. We use API similar to MPI, so we have broadcast and reduce, but you also have, you can register for the signal, so you can query, what is the topology, and you can register more machines to the communication group, or if machine fails, the whole communication group doesn't fail, so you have to decide what to do in this case. You can add more resources and repeat the last iteration, something like that. So again, the two most important operations that we use a lot in tensor factorization is broadcast and reduce. So broadcast is basically, you have one machine that contains the data, and you want to propagate it to all worker nodes. In our case, this is basically distributing a model. And if you have one node sending the same data to all other nodes, it's basically lots of connections, and it takes a while. So you can do lots of optimizations here. First of all, you can have peer-to-peer communication. You can build a tree, so it's usually a binary tree or Fibonacci tree, and have peer-to-peer sends to broadcast this model faster. Similarly, for reduce, it's like the opposite operation, where you have chunks of results that you want to collect, and you usually perform some aggregation as you go, and eventually one receiver gets the data. So in case of machine learning, it will be some updating to the gradients and stuff like that. In our case, it will be rows of the matrix that we produce at each step. And again, we can form the tree, we can do pipelining, and this is how it looks in code. Yeah, in code it's very simple. So any Java serializable object. So in our case, we use JBlast matrices. So you can just send the matrix and broadcast it to all the nodes. And when you're expecting the data, so this is the master node. So we just wait for all the data to be assembled, and we get the data. So that's pretty much it. So we have a new algorithm that works fairly well and looks very promising. It's fast. We tested it on not so big corpus, but like moderate, and it showed good results in terms of performance and also in terms of accuracy. And best of all, and very dear to my heart of an engineer, the code is very, very compact, and we have a very clear separation of math and control flow. So, and using the REEF library, we were able to get rid of lots of boilerplate code that I would have written otherwise. So that's it. And also, the whole thing is open sourced. So tensor factorization, I really, really hope that it will be open source for the conference. It's on the last stages of the approval, and it will be on GitHub under MIT license, so you're most welcome to take a look as soon as it is available. REEF is open source, so it is currently Apache incubator project, but it has a very strong developer base, and there are some projects internally at Microsoft and outside of Microsoft that use REEF, so it's pretty mature already, but it also being developed actively, so the new features get added every day. So just 2 weeks ago, we released a new version, and most of the features were on the .NET side of the world. So you can actually, using REEF, you can mix and match your .NET and Java code. So say, for example, you can have workers written in C#, and the driver will be in Java, and you can say, you can distribute configuration like from Java to C# and back, and you can send messages, and for example, if exception is thrown from the C# code, it will be serialized, and you'll get the corresponding message in Java driver. And it's all on Apache, because it's open source project, it's on Apache Central, on Maven Central, so all you have to do, you just add the few lines into your pom.xml, and you're done. You can use it. So you don't need REEF cluster. It's just a jar, and you can run it on Yarn. Okay, so please go check it out, use it. Better yet, contribute your code to it. Tell us your success stories, or better yet, join Microsoft. We have an awesome team. Half of our team is in Mountain View, actually. Another half is in Redmond. So you can choose which campus you want to work with. And in Redmond, we have water, and you don't. And I can actually, yes. So, and you're most welcome to, and you can buy a house, actually. So, yes. So you're most welcome to ask me anything if you bump into me outside of this room. And yeah, ask your questions. Thank you very much. Yeah, go ahead.
Have you considered using a high-level library such as Spark or GRAPH?
It's actually a little bit overkill for us because, well, first, like REEF actually does what we need, so we don't have to we don't have to pull in all those dependencies. So and also, like in the longer term, we are actually, like this is one area of research, is we want to be elastic and fault aware for machine learning algorithms. And REEF actually gives you a lot of control in this area. So like say if you're doing batch gradient descent and one of the node fails, well, actually you can probably continue, right? Especially if your algorithm already converged, you don't have to allocate, because it will take a while, right, to allocate a new node, wait for Yarn to allocate it, and all this, like submit the job there. Probably by the time you get this node, you'll be done with the computation anyways, right? And similarly, for many algorithms, you can start with a very small sample and make rapid progress, so you can ramp up with a very few nodes and then add nodes as you go. So we actually very interested in that kind of computation. So, and as far as I know, Spark does not provide much leverage. Well, they're working on this, but it wasn't there when we started. So that's one explanation. Go ahead. You can yell from there, and I'll repeat the question.
So I had a question about the broadcast.
Uh-huh.
You mentioned that there were the optimization strategies, like using a tree or peer-to-peer. Does REEF have functions to support those various things, or is REEF say we have the capability to do that?
So the question is, in broadcast and reduce, we mentioned that there are certain optimizations possible, like using a broadcast tree. So the question is that just a possible optimization, or is that something really implemented in REEF? The question is, it is implemented in REEF. So right now we have, so in MPI you usually have a choice. So usually you configure your job and you say like, use like one node make one node connect to all other nodes, or you use a binary tree, or you use Fibonacci tree. In our case, we have binary tree right now. Very likely we will add Fibonacci tree soon, and probably at some point we'll allow user to actually pick.
And you mentioned a parameter server. Is it the top? I don't know. Is that something
This parameter server. So I mentioned it basically like what people have to do if they use algorithms like Gibbs sampling or Monte Carlo methods. In our case, we do not need parameter server because we share very little information. But in general, REEF would be ideal framework to implement your parameter server if you want to have parameter server on Yarn. Sure. We have 5 more minutes, yeah, or 5 minutes of awkward silence.
How do you evaluate your topic models? How do you know how good they are?
Oh,
and
that's
how
a
many
very good
topics
question.
you
Yeah,
need?
so the question is, how do we evaluate the topic models? So typically, so we use the log perplexity on the held out part of corpus, but I'm an engineer, so I'm afraid that I won't give you details, but it's a standard way of comparing distributions, and I believe we just follow the paper for, there's online LDA by Hoffman and the team, and I believe we just implement their model. Oh, very good question. This is how many topics we used. This is where I have to confess. We used just 100 topics, which is nothing, right? So, but the idea was to just, we plan to use a bigger corpus, like PubMed size corpus, and ideally we want to test it on like millions of topics, and we will do this. By the time I submitted the proposal, we're not there yet. But nothing prevents us from doing this. We just need to allocate the class. So it's mostly like, administrative issues rather than technical. So the code itself, I'm pretty sure it can run on millions of topics because it's highly parallelizable. And also, we'll probably try it on things different from topic modeling, like say for community detection and graphs. So there's lots of work that is to be done there, and hopefully we'll give you more news on the next Strata or Hadoop Summit. Yes? Anyone else? 1, 2, 3. All right, go ahead.
What about
Hierarchical topic modeling. The question is, I don't know. I'm an engineer. So yes. So yes, there's those Chinese restaurant processes and like hierarchical topics where you, in general, like the idea is that you're not limited to the number. Like you don't specify in advance how many topics you want. So I don't know how to do that in the tensor setting, honestly. You have to talk to Anima. She's a pioneer of tensor methods for all this stuff. All right, I guess that's it. Thank you very much, guys. And stop by. Bring me your resumes.